Jupiter is the largest world in our solar system, a planet so immense that every other world we know could fit inside it with room to spare. More than 1,000 Earths could nestle within its curved boundaries, lost like grains of sand inside a great balloon. For centuries, we have gazed at its swirling bands of color, its famous storms, its pale moons crossing its face like tiny shadows. Astronomers have tracked its movements through the night sky. Artists have painted its portrait in oils and watercolors. Dreamers have wondered what secrets it might hold in its heart. But all of that beauty, all of those swirling colors and raging tempests, exists only at the surface. Beneath those clouds lies a realm of crushing darkness that no human eye has ever seen. The colors we admire are merely a mask, a thin painted veil stretched across something far more ancient and strange. Until recently, we had no way to peer inside, but a small spacecraft circling this giant in patient loops has finally begun to reveal what hides in Jupiter's deep atmosphere. Before we drift into the giant's depths, if these cosmic journeys help you find peace, please consider liking this video and subscribing to join our sleepy community. Now, wherever you are, let yourself settle in. Perhaps you are lying in bed, the day's worries slowly releasing their grip. Perhaps you are resting on a couch, eyes growing heavy as the evening deepens around you. Wherever you find yourself, let your breathing slow. Let your shoulders drop. And imagine for a moment that you are floating in the cold silence of space, approaching a world unlike anything on Earth. A world where the sky never ends, where storms larger than our entire planet rage for centuries without rest, where the very meaning of solid ground dissolves into something strange and unfamiliar. This is Jupiter, the king of planets, the ancient guardian of our solar system. And tonight, we are going to sink beneath its clouds and discover what secrets it has been hiding for 4.5 billion years. To understand what makes Jupiter so remarkable, we need to first appreciate just how different it is from the world we call home. Earth is a rocky planet. We walk on solid ground. We build our homes on foundations of stone and soil. When we dig down, we find more rock, then eventually the molten layers of our planet's interior. But there is always something solid beneath our feet, something we can touch and stand upon. Jupiter has no solid ground. There is no surface to land on, no rocky terrain, no familiar landscape waiting below. If you tried to descend through the clouds, you would simply keep falling, sinking through ever thicker layers of gas with no bottom in sight. The entire planet is a vast ocean of atmosphere that grows denser and heavier the deeper you go. There is no clear line where the sky ends and the planet begins. Instead, everything blurs together in a continuous gradient from thin gas to thick gas to something that behaves more like liquid than air. The colorful clouds we see in photographs are just the thin outer skin of something far more strange and far more immense. Those bands of orange and white and brown that make Jupiter so recognizable in pictures represent only the outermost layer of the atmosphere. Below them, hidden from our view, the atmosphere continues downward for thousands of miles. It changes in ways that seem almost impossible to imagine. Pressures build to levels that would crush any machine we could build. Temperatures rise to thousands of degrees, and the very nature of matter itself begins to transform into something we have never seen on Earth. For most of history, this interior remained a complete mystery. We could watch the storms spin across Jupiter's face through our telescopes. We could measure how fast the planet rotates by tracking features in its cloud bands. We could calculate its mass by observing how strongly it pulls on its moons. But we could not see through those clouds. They blocked our view, like a curtain drawn across a window, hiding whatever lay beneath in perpetual shadow. Scientists could only guess at what the interior might be like. They built mathematical models, trying to predict how gases would behave under such extreme conditions. They studied the planet's gravitational pull and its magnetic field, searching for clues about its hidden structure. But without a way to actually peer beneath the clouds, their theories remained unconfirmed. Jupiter kept its secrets locked away, visible to us only as that bright wandering star our ancestors had watched for thousands of years. Then, in 2011, something changed. A spacecraft lifted off from Cape Canaveral in Florida, beginning a journey that would take it nearly 2 billion miles across the emptiness of space. It was called Juno, named after the goddess from Roman mythology, who could see through clouds to witness the truth hidden beneath. The name was fitting, because that was exactly what this spacecraft was designed to do. Juno traveled for 5 years through the solar system, swinging past Earth once to gain speed, before finally arriving at Jupiter in July of 2016. It had been sent by NASA with a mission both simple in concept and extraordinary in ambition. Scientists wanted to understand what Jupiter is made of and how it works from the inside out. They wanted to finally answer questions that humans have been asking for generations. What lies beneath those beautiful clouds? How deep do the storms go? What is the planet's core made of? And how did this giant world come to exist in the first place? To accomplish these goals, Juno was equipped with instruments unlike anything we had sent to Jupiter before. Most importantly, it carried a microwave radiometer, a device that could detect a form of light invisible to human eyes. Microwaves can pass through the upper clouds that block visible light, revealing what lies beneath. For the first time in history, we had a way to peer into the hidden layers of the giant planet. Juno does not orbit Jupiter the way most spacecraft orbit planets. Instead of circling around the equator, it swoops over the poles in long, stretched-out ellipses. Each orbit takes about 53 days to complete. The spacecraft spends most of that time far from Jupiter, out where the radiation is less intense and its instruments can rest. But once every orbit, it dives in close, skimming just a few thousand miles above the cloud tops before swinging back out into safer space. These close passes are when the magic happens. As Juno races over Jupiter's surface, it gathers data with all of its instruments at once. It maps the planet's magnetic field. It measures variations in gravity. It captures images in visible light and infrared and ultraviolet. And most importantly, it peers beneath the clouds with its microwave eyes, building up a picture of what lies below, layer by layer. What scientists have found in the years since Juno arrived has reshaped our understanding of this giant world. Some discoveries confirmed theories that had been proposed decades ago. Others revealed surprises that no one had predicted. Together, they paint a portrait of a planet far more complex and far more violent than we ever imagined. Let yourself drift now as we begin our descent. Imagine that you are aboard a vessel of pure thought, immune to the crushing pressures and searing temperatures below. Imagine that you can fall through the clouds without harm, witnessing everything as you sink ever deeper into the giant's embrace. The journey will take us through layers of increasing strangeness, through weather systems that dwarf our entire world, through regions where matter itself transforms into exotic states. And eventually, we will reach the mysterious heart of Jupiter, where secrets 4.5 billion years old still wait to be understood. The first thing you notice as you approach Jupiter from space is the sheer size of it. Earth is a small blue marble, easily held in the mind's eye. Jupiter is something else entirely. It takes up the sky, growing larger and larger as you approach, until it stops feeling like a planet at all. It feels like a wall, a curved wall of swirling colors stretching in every direction as far as you can see. The planet rotates quickly, faster than any other planet in our solar system. A day on Jupiter lasts only about 10 hours, which means the clouds at its equator are whipping around at nearly 28,000 miles per hour. This rapid rotation creates the bands that make Jupiter so recognizable. The lighter zones and darker belts that wrap around the planet are not painted on. They are actual streams of atmosphere flowing in different directions, sheared into stripes by the planet's spin. These bands have been observed for as long as humans have had telescopes powerful enough to see them. Early astronomers noticed that the zones and belts shift slightly over time, growing wider or narrower, brighter or dimmer. Storms appear and disappear. Colors change from year to year, but the overall pattern remains remarkably stable. Jupiter's face looks much the same today as it did when Galileo first pointed his telescope at it over 400 years ago. For a long time, scientists assumed that these bands were shallow features. They thought the colorful stripes existed only in the upper atmosphere, driven by solar heating and perhaps extending down a few hundred miles at most. Below that, they assumed, the atmosphere would become more uniform, settling into a featureless ball of compressed gas. Juno proved this assumption wrong. As the spacecraft measured tiny variations in Jupiter's gravitational pull, it detected something unexpected. The gravity was not uniform across the planet's surface. As Juno flew over different bands, it felt slightly stronger or weaker tugs. These variations were tiny, but they carried enormous significance. They meant that the bands were not just surface features. They extended deep into the interior, far deeper than anyone had predicted. We now know that Jupiter's belts and zones reach down at least 1,800 miles beneath the visible cloud tops. That is roughly the distance from New York to Denver. The streams of atmosphere that create those colorful bands are not shallow weather patterns. They are fundamental structures of the planet itself. Rivers of gas flowing in opposite directions for thousands of miles both across and down. Below this depth, the atmosphere finally becomes more uniform. The winds decrease, and the banded structure fades away. But that transition zone marks a boundary between two very different regions of Jupiter's interior. Above it, the atmosphere flows in organized streams, driven by forces we do not yet fully understand. Below it, something else entirely is happening. To understand what lies below the bands, we need to think about pressure. On Earth, we live at the bottom of an ocean of air. The atmosphere above us pushes down with a weight of about 14.7 pounds on every square inch of surface. We call this one atmosphere of pressure, and our bodies are so accustomed to it that we rarely notice it at all. Now imagine going deeper. In the ocean, pressure increases rapidly as you descend. Every 33 feet of depth adds another atmosphere of pressure. At the bottom of the Mariana Trench, the deepest point in Earth's oceans, the pressure reaches about 1,000 atmospheres. Submarines that venture there must be built with incredibly thick hulls to withstand the crushing force. On Jupiter, the pressures are beyond anything we experience on Earth. As you sink through the atmosphere, the weight of all the gas above you presses down with ever-increasing force. Just a few hundred miles below the visible clouds, the pressure already exceeds anything in Earth's oceans. Keep going, and it climbs to thousands of atmospheres, then tens of thousands, then hundreds of thousands. At these extreme pressures, gases stop behaving the way we expect. The hydrogen that makes up most of Jupiter's atmosphere begins to change. The molecules are squeezed so close together that they transition from gas into liquid without ever passing through a distinct boundary. There is no surface of a liquid hydrogen ocean, no clear line where gas ends and liquid begins. Instead, the transition is gradual, a continuous increase in density as you sink deeper and deeper. This liquid hydrogen layer extends for thousands of miles beneath the cloud tops. It is an ocean unlike anything on Earth, an ocean without a surface or a floor, existing in 3 dimensions as a vast sphere of compressed fluid surrounding the planet's core. The temperatures here are searing hot, thousands of degrees, but the pressure is so immense that the hydrogen remains liquid rather than evaporating into gas. And still, if you continue sinking, the pressure would keep building. Eventually, at about 12,000 miles below the cloud tops, something remarkable happens. The pressure reaches approximately 2 million atmospheres, and the liquid hydrogen undergoes another transformation. The molecules are squeezed so tightly that electrons begin to break free from their atoms. The hydrogen becomes a conductor of electricity. It stops behaving like the hydrogen we know and starts behaving like a metal. Scientists call this strange substance metallic hydrogen. It is one of the most exotic materials in the universe, and it cannot exist under normal conditions. No laboratory on Earth can recreate the pressures needed to make it. We can only study it through theory and computer simulations, inferring its properties from the way Jupiter and Saturn behave. But we know it must exist, because only metallic hydrogen can explain the incredibly powerful magnetic field that surrounds Jupiter. Jupiter's magnetic field is the largest structure in our solar system after the Sun itself. It extends millions of miles into space, far beyond the orbits of the planet's moons. If we could see it with our eyes, it would appear larger than the full moon in Earth's sky. This enormous magnetic bubble is generated deep within Jupiter's interior, in that layer of metallic hydrogen where electrical currents flow through a planet-sized dynamo. The field is not only vast, but also incredibly strong. At the cloud tops, it measures about 20 times the strength of Earth's magnetic field. But near the planet's poles, where Juno makes its closest passes, the field becomes even more intense. Scientists were surprised to find that the magnetic field is lumpy and irregular, not the smooth dipole they expected. There are spots where the field is concentrated into patches of intense strength, and other places where it seems to weaken unexpectedly. One of the most mysterious of these patches has been nicknamed the Great Blue Spot. This is not a visual feature like the Great Red Spot. You cannot see it in photographs of Jupiter's clouds. Instead, it is a region of intense magnetic activity located near Jupiter's equator, visible only in the data from Juno's magnetometer. The magnetic field there behaves strangely, dipping and swirling in patterns that do not match the rest of the planet. Scientists believe the Great Blue Spot may be caused by deep flows of metallic hydrogen beneath Jupiter's surface. Just as currents of molten iron in Earth's outer core generate our planet's magnetic field, currents of metallic hydrogen generate Jupiter's. But while Earth's core is relatively simple, Jupiter's interior seems to harbor complex flows and eddies that create localized regions of magnetic intensity. The Great Blue Spot is slowly drifting eastward, moving about 2 inches per second relative to the rest of the planet. This may not sound like much, but over the years that Juno has been observing, the drift is measurable. The spot has also changed shape slightly, suggesting that the deep currents creating it are not static, but evolving over time. All of this magnetic complexity hints at a turbulent interior far below the visible surface. Jupiter may look serene in photographs, with its smooth bands and slowly spinning storms. But beneath those clouds, immense forces are at work. Rivers of metallic hydrogen flow through crushing darkness, generating fields that reach across the solar system. It is a hidden engine of almost incomprehensible power, driving processes we are only beginning to understand. Let us pause here in our descent and return to the upper atmosphere, where the weather phenomena that make Jupiter famous play out across skies larger than worlds. The storms of Jupiter have fascinated observers ever since telescopes revealed them over 4 centuries ago. But it was Juno that finally showed us how deep these tempests reach and how they connect to the processes occurring far below. The most famous of Jupiter's storms needs no introduction. The Great Red Spot has been observed continuously since at least 1830, and there are records that may show it as far back as 1665. It is the largest storm in the solar system, a hurricane that could swallow Earth whole with room to spare. At its widest, it has measured over 25,000 miles across, though in recent decades it has been shrinking gradually. The Great Red Spot rotates counterclockwise, completing one full rotation in about 6 Earth days. Winds at its edges blow at over 400 miles per hour, creating a vortex of incredible violence. The red color comes from chemicals in the atmosphere that are carried upward by the storm and transformed by solar radiation, though scientists still debate exactly which chemicals are responsible. For a long time, astronomers wondered how deep the Great Red Spot extended. Was it a shallow weather system, like hurricanes on Earth, that span only the upper few miles of atmosphere? Or did it reach much deeper into the planet's interior? The answer came from Juno's microwave instrument, which could peer beneath the cloud tops and map the storm's structure. The Great Red Spot extends downward at least 200 miles, and possibly as much as 300 miles. That is deeper than the distance from Earth's surface to the edge of space. The storm is not just a swirl of clouds. It is a column of rotating atmosphere that reaches deep into Jupiter's interior, anchored by forces we do not yet fully understand. Its roots extend into regions where the pressure is crushing and the temperature is already rising toward the searing levels found deeper within. This depth helps explain why the storm has lasted so long. On Earth, hurricanes lose strength when they move over land or cold water because they depend on warm ocean surfaces for their energy. The Great Red Spot has no such limitation. It draws energy from the heat rising from Jupiter's interior, a virtually unlimited source that has powered the storm for centuries. But the Great Red Spot is not the only storm on Jupiter. The planet is covered with smaller vortices, some white, some brown, some reddish, all of them spinning across the banded landscape of the atmosphere. Many of these storms are larger than Earth themselves. They form, merge, split apart, and dissipate over timescales ranging from weeks to centuries. Jupiter's atmosphere is in constant motion, a dynamic canvas where weather systems are born and die in an endless cycle. Juno discovered something remarkable about the storms near Jupiter's poles. At both the North and South poles, there are clusters of cyclones arranged in geometric patterns. The North Pole features 8 cyclones surrounding a central one, arranged roughly in an octagonal shape. The South Pole has 5 cyclones around a central one, forming a pentagonal pattern. These arrangements have remained stable for the years that Juno has been observing them, rotating slowly but maintaining their positions relative to each other. No one predicted these polar cyclones before Juno arrived. They are each thousands of miles across, comparable in size to the continental United States. The winds within them blow at hundreds of miles per hour, and somehow, despite the chaos and turbulence of Jupiter's atmosphere, they have arranged themselves into stable geometric patterns and stayed that way for years. Scientists are still trying to understand how these cyclone arrangements remain stable. On Earth, storm systems move and change constantly, pushed by jet streams and shaped by the interaction between ocean and atmosphere. Jupiter has no ocean surface to stabilize its weather patterns, yet these polar cyclones appear to be locked in place by forces we do not yet fully comprehend. The cyclones are visible in infrared images as warm spots against the cooler background of the polar atmosphere. They rotate in the opposite direction from the planet itself, spinning against Jupiter's rapid rotation like eddies in a swift river. Their boundaries are remarkably sharp, with clear edges separating each cyclone from its neighbors. This suggests that some force is preventing them from merging together or drifting apart. One theory proposes that the cyclones represent a stable state that naturally emerges from the fluid dynamics of Jupiter's atmosphere. When conditions are right, vortices may spontaneously arrange themselves into patterns that balance the forces between them. It is similar to the way soap bubbles pack together, finding configurations that minimize their total energy. The cyclones may have settled into their geometric arrangements because those arrangements represent the most stable state available to them. Another mystery Juno has helped unravel involves lightning on Jupiter. We have known since the Voyager missions in 1979 that lightning exists in Jupiter's atmosphere. Flashes were detected on the night side of the planet, brief bursts of light indicating electrical storms in the clouds. But the lightning seemed to occur mainly near the poles and in certain belts of the atmosphere. The equatorial regions appeared strangely quiet. This was puzzling because on Earth, lightning is most common in the tropics, where warm, moist air rises vigorously and creates the towering thunderstorms that generate electrical charges. If Jupiter's atmosphere worked the same way, lightning should be common near the equator, where the sunlight is strongest. Instead, it seemed concentrated at higher latitudes. Juno resolved this puzzle by detecting a new kind of lightning that previous missions had missed. The spacecraft found high-altitude lightning in Jupiter's upper atmosphere, in regions where ammonia ice exists, rather than water ice. These shallow lightning flashes are different from the deep lightning detected before. They occur in a layer of the atmosphere where temperatures are cold enough for ammonia to freeze, but not cold enough for water to exist in solid form. The discovery of shallow lightning reveals that Jupiter's atmospheric chemistry is more complex than scientists had realized. Electrical storms can form in multiple layers of the atmosphere, powered by different chemical processes at different depths. Water-based thunderstorms occur deeper down, where water vapor can condense. Ammonia-based storms occur higher up, in the frigid upper clouds. This layered structure of storms helps explain why Jupiter's lightning distribution differs from Earth's. The deep water-based lightning does tend to concentrate near the poles, where Jupiter's internal heat drives more vigorous convection. But the shallow ammonia lightning can occur anywhere, including near the equator. The two types of lightning tell different stories about different layers of the atmosphere. Juno also discovered something unexpected about the ammonia in Jupiter's atmosphere. Scientists had assumed that ammonia would be distributed fairly, uniformly throughout the upper layers, mixed evenly by the constant churning of the atmosphere. Instead, Juno found that ammonia concentrations vary dramatically from place to place and from depth to depth. In some regions, ammonia appears to be depleted in the upper atmosphere, as if something has carried it down to lower levels. In other regions, it is enriched, suggesting upwelling from below. The pattern suggests a vast circulation system in which ammonia-laden air sinks in some places and rises in others, similar to the way water vapor cycles through Earth's atmosphere, but on a much larger and more complex scale. This ammonia circulation may be connected to the mushball theory, one of the more intriguing ideas to emerge from Juno's observations. Scientists propose that in certain regions of Jupiter's atmosphere, ammonia mixes with water to form a slushy mixture that coats hailstones. These ammonia-rich mushballs fall through the atmosphere like giant slushy hailstones, carrying ammonia from the upper clouds down to deeper layers where it dissolves back into the surrounding gas. If the mushball theory is correct, it would explain why ammonia is depleted in parts of Jupiter's upper atmosphere. The ammonia is being transported downward by falling chunks of ammonia water slush, a form of precipitation unlike anything on Earth. It would also help explain the complex layering of storms and the unusual distribution of chemicals throughout the atmosphere. Let us continue our imaginary descent now, sinking below the weather layer into regions where storms no longer rage and the atmosphere becomes increasingly calm. The pressure builds with every mile we drop, the temperature rises steadily, and the nature of the material around us begins to change. We are entering the deep atmosphere of Jupiter, the realm that Juno's microwave eyes have been mapping since the spacecraft arrived. The first few hundred miles below the visible clouds still contain the banded structure we observe from space. The winds continue blowing, though they gradually weaken with depth. The temperature rises, climbing from the relatively cold cloud tops toward warmer regions below. At the cloud tops, temperatures hover around minus 160 degrees Fahrenheit, but that changes quickly as you descend. Within just a few tens of miles, the temperature has risen above water's freezing point. Within 100 miles, it has reached the boiling point, and it keeps climbing from there, driven by the immense internal heat that Jupiter radiates into space. Unlike Earth, which receives most of its heat from the Sun, Jupiter generates more energy than it receives. The planet is still slowly contracting from its formation, converting gravitational energy into heat that leaks outward through the atmosphere. This internal heat is what drives Jupiter's weather. The Sun provides some energy to the upper atmosphere, creating the temperature differences that power surface winds. But the deep circulation of the atmosphere is driven from below by heat rising from the planet's interior. Jupiter is like a pot of water slowly boiling, with convection currents carrying hot material upward, while cooler material sinks to replace it. As you continue sinking, the atmosphere around you grows thicker and thicker. The hydrogen and helium that make up most of Jupiter's mass are squeezed ever more tightly together. At the cloud tops, the atmosphere is less dense than Earth's sea-level air. But by the time you have descended a few 100 miles, it has become denser than water, and still you sink, with the density continuing to increase mile after mile. There is no clear boundary between gas and liquid in this region. Unlike on Earth, where water has a distinct surface separating liquid from vapor, Jupiter's hydrogen transitions smoothly from one state to another. The atmosphere simply gets denser and denser until it stops behaving like gas and starts behaving like liquid. This happens at depths where the pressure reaches several 100,000 atmospheres, far beyond anything in our everyday experience. The liquid hydrogen layer extends for thousands of miles, a vast ocean without shores or surface. If you could swim through it, you would find it warm and increasingly dense as you descended. The pressure would be fatal to any physical body, of course. But in our imagination, we can drift through these regions unharmed, observing the gradual changes that occur as we approach the planet's mysterious core. At about 12,000 miles below the cloud tops, the liquid hydrogen undergoes its dramatic transformation into metallic hydrogen. This is not a sharp boundary either, but a gradual transition that occurs over hundreds of miles. The hydrogen becomes increasingly conductive until it behaves more like molten metal than like any liquid we know on Earth. This metallic hydrogen layer is the engine that generates Jupiter's enormous magnetic field. As the planet rotates, the metallic hydrogen rotates with it, and electrical currents flow through the conducting fluid. These currents create magnetic fields, which in turn influence the currents, setting up a self-sustaining dynamo that has been running for billions of years. The magnetic field generated by this dynamo is incredibly complex. Unlike Earth's relatively simple dipole field, Jupiter's field has multiple poles and irregular patterns. Juno's detailed measurements have revealed a magnetic landscape of surprising intricacy, with concentrated patches of field strength and unexpected weaknesses in other areas. One of the reasons for this complexity may be the way the metallic hydrogen layer interfaces with the regions above and below it. The transition from molecular liquid hydrogen to metallic hydrogen is not clean and simple. There may be mixing and turbulence at the boundary, creating eddies and flows that disturb the regular patterns of the dynamo. The result is a magnetic field that varies from place to place across Jupiter's surface. Deep beneath the metallic hydrogen layer lies the region of greatest mystery, Jupiter's core. For decades, scientists debated whether Jupiter had a core at all. Some models suggested the planet was essentially uniform throughout, with hydrogen gradually transitioning to heavier elements without any distinct central region. Other models proposed a dense rocky core at the center, similar to the cores that may exist within Earth and the other terrestrial planets. Juno's gravity measurements have helped settle this debate, though the answer turned out to be more complex than anyone anticipated. Jupiter does have a core, but it is not the compact rocky sphere that many expected. Instead, the core appears to be diffuse and fuzzy, a region where heavy elements are mixed with hydrogen rather than concentrated into a distinct ball. Scientists describe this as a dilute core, a central region enriched in elements heavier than hydrogen and helium, but not sharply separated from the surrounding layers. The heavy elements, which include things like rock, iron, and water, extend outward from the center and gradually thin out as you move away. There is no clear edge to the core, just a gradual decrease in the concentration of heavy materials. This dilute core may be the result of a cataclysmic event early in Jupiter's history. One leading theory suggests that a large protoplanet, perhaps several times the mass of Earth, collided with Jupiter not long after the giant planet formed. The impact would have disrupted any compact core that had already accumulated, mixing the heavy elements with the surrounding hydrogen and creating the fuzzy structure we observe today. If this theory is correct, Jupiter still bears the scars of that ancient collision, preserved in its internal structure 4.5 billion years later. The event would have released enormous energy, temporarily heating the planet's interior and creating shockwaves that propagated outward through the atmosphere. But over the eons, Jupiter has settled back into equilibrium, slowly cooling and contracting while that diffuse core remains as evidence of its violent youth. The temperature at Jupiter's core may reach 45,000 degrees Fahrenheit, hotter than the surface of the Sun. The pressure there approaches 100 million atmospheres, greater than anything else in the solar system outside the Sun itself. Under such extreme conditions, matter behaves in ways that are difficult to study or even imagine. The core is a realm of exotic physics, where the ordinary rules of chemistry and mechanics break down. No probe will ever reach Jupiter's core. The pressures and temperatures are simply too extreme for any material we know how to make. Even if we could build something strong enough to withstand the conditions, it would have no way to transmit information back to us through thousands of miles of crushing atmosphere. The core will remain forever out of reach, knowable only through the indirect measurements that spacecraft like Juno can make from orbit. But those indirect measurements have already taught us an enormous amount. By carefully tracking Juno's orbit and measuring the tiny variations in Jupiter's gravitational pull, scientists can infer the distribution of mass within the planet. By mapping the magnetic field, they can deduce the flows of electrically conducting material deep beneath the surface. And by peering through the clouds with microwave instruments, they can directly observe the temperature and composition of the upper atmosphere down to depths of several hundred miles. Together, these measurements paint a portrait of a planet far more dynamic and complex than the serene giant we see in photographs. Jupiter is not just a ball of gas spinning in the void. It is a world of layers and boundaries, of chemical transformations and extreme physics, of ancient scars and ongoing processes. It is a natural laboratory for studying conditions that cannot exist anywhere on Earth. Let us rise now from the crushing depths and return to the upper atmosphere, where we can observe some of the most beautiful and mysterious phenomena that Juno has revealed. Jupiter's weather is dramatic enough when viewed from afar, but Juno's close-up perspective has shown us details that previous missions could never resolve. Jupiter's auroras are among the most spectacular in the solar system. Like the northern and southern lights on Earth, they are caused by charged particles from space funneling down along magnetic field lines and exciting gases in the upper atmosphere. But Jupiter's auroras are far larger, far brighter, and far more complex than anything on our home planet. Earth's auroras are powered primarily by the solar wind, the stream of charged particles constantly flowing outward from the Sun. When solar storms send particularly intense bursts of particles toward Earth, the auroras brighten and expand, sometimes becoming visible from lower latitudes than usual. But the connection between solar activity and auroral displays is relatively straightforward. Jupiter's auroras are different. Some of the energy driving them does come from the solar wind, but much of it originates from a source unique to Jupiter, its volcanic moon Io. We will speak more about the Galilean moons later, but for now, it is enough to know that Io is the most volcanically active body in the solar system. Its eruptions spray sulfur and other materials into space, creating a donut-shaped ring of plasma that surrounds Jupiter. This plasma ring, called the Io torus, is the source of much of the material that powers Jupiter's auroras. As Jupiter rotates, its enormous magnetic field sweeps through the torus, accelerating charged particles to tremendous speeds and flinging them along field lines toward the planet's poles. When these particles strike the upper atmosphere, they create auroral glows that can be 100 times brighter than Earth's northern lights. Juno has observed Jupiter's auroras in unprecedented detail, revealing structures that were invisible to previous missions. There are main auroral ovals near both poles, similar to the auroral ovals on Earth but much larger. But there are also countless smaller features, bright spots, swirls and streamers that change from minute to minute as the magnetic field and particle flow shift. Some of the brightest auroral spots correspond to the magnetic footprints of Jupiter's largest moons. As Io, Europa, Ganymede, and Callisto move through Jupiter's magnetic field, they create disturbances that propagate down to the planet's atmosphere. The result is bright auroral spots that track across Jupiter's polar regions, tracing out the orbital positions of the moons in glowing light. The physics of Jupiter's auroras is still not fully understood. The processes that accelerate particles to such high energies, the mechanisms that create specific auroral structures, the ways in which the auroras respond to changes in the solar wind and the Io torus. All of these are active areas of research. Juno's observations have provided crucial data, but they have also raised new questions that scientists are still working to answer. One surprising discovery involves the nature of the particles that create the auroras. On Earth, most auroral light is produced by electrons descending from space into the atmosphere. Scientists expected Jupiter's auroras to work similarly, with electrons as the primary carriers of energy. But Juno found that protons and other ions play a much larger role than anticipated. The chemistry and physics of Jupiter's auroras may be fundamentally different from what happens on Earth. The auroras also reveal information about Jupiter's magnetic field that cannot be obtained any other way. By mapping where the auroral emissions occur and how they change over time, scientists can trace the magnetic field lines that guide particles into the atmosphere. This provides an additional check on the direct magnetic field measurements and helps confirm the complex, irregular structure of the field. Beyond the auroras, Juno has revealed new details about the composition of Jupiter's atmosphere. The planet is made primarily of hydrogen and helium, the two lightest elements, which together account for more than 99% of its mass. But trace amounts of other substances give the atmosphere its colors and drive its complex chemistry. Ammonia is one of the most important trace gases, and Juno has mapped its distribution in detail. As mentioned earlier, the ammonia is not uniformly mixed, but shows complex patterns of enrichment and depletion at different depths and latitudes. These patterns are connected to the circulation of the atmosphere, with ammonia being transported by rising and sinking currents. Water is another crucial component, though it exists only in the deeper layers of the atmosphere where temperatures are high enough for it to remain gaseous rather than frozen. Jupiter's water content has been a puzzle for decades, with different measurements giving wildly different results. The Galileo probe, which descended into Jupiter's atmosphere in 1995, measured far less water than expected in the region where it entered. But that region turned out to be an unusually dry hotspot, not representative of the planet as a whole. Juno has attempted to measure water more comprehensively using microwave observations that can peer to depths where water exists in gaseous form. The results suggest that Jupiter has roughly 2 to 3 times as much oxygen in the form of water as the Sun. This is significant because it tells us something about how the planet formed and whether it migrated from elsewhere in the solar system. The ratio of different elements in Jupiter's atmosphere serves as a fossil record of the conditions that existed when the planet was born. Elements that could only be delivered by solid objects, like rock and ice, tell us about the materials that Jupiter accumulated in its early history. If Jupiter formed very close to the Sun and stayed there, its composition would differ from a planet that formed farther out and migrated inward. The current evidence suggests that Jupiter did not migrate dramatically, but formed approximately where we find it today, in the outer reaches of the solar system where ice was abundant. The oxygen enrichment detected by Juno supports this picture, suggesting that Jupiter accumulated substantial amounts of water ice as it grew. But the story is complicated by the fact that different elements show different levels of enrichment, hinting at a more complex formation history than simple models predict. Sulfur, phosphorus, and other elements also appear in Jupiter's atmosphere, contributing to the complex chemistry that produces the planet's colors. The exact chemical reactions responsible for the orange and red hues of Jupiter's clouds have been debated for decades. Sulfur compounds were long thought to be the primary source of color, but recent research suggests that organic molecules created by solar radiation may play an important role. When sunlight strikes the upper atmosphere, it breaks apart some of the ammonia and other molecules, creating reactive fragments that can combine in various ways. Some of these reactions produce complex organic compounds, similar to the brown and orange materials seen in laboratory simulations. These compounds may coat ice crystals in the upper clouds, giving Jupiter its characteristic tawny appearance. The Great Red Spot may owe its distinctive color to similar processes. The storm reaches so high into the atmosphere that the materials within it are exposed to particularly intense solar radiation. Over centuries, the chemical reactions driven by this radiation have produced a concentration of colored compounds that distinguishes the storm from the paler clouds around it. As the Great Red Spot has shrunk in recent decades, its color has actually intensified, perhaps because the same amount of colored material is now concentrated in a smaller area. Let us take a moment now to consider the broader context of Jupiter's place in our solar system. This giant planet is not just an object of scientific curiosity, though it is certainly that. It is also a gravitational anchor that has shaped the history of every world in our cosmic neighborhood. Jupiter was one of the first planets to form after our Sun ignited, perhaps within just a few million years of the solar system's birth. It grew rapidly, gathering gas from the nebula that surrounded our young star. Its gravity was strong enough to capture hydrogen and helium directly from the surrounding cloud, allowing it to grow far larger than the rocky planets that would eventually form closer to the Sun. As Jupiter grew, its gravity began to influence everything around it. It stirred up the orbits of smaller bodies, flinging some into the outer solar system and pulling others inward toward the Sun. It may have prevented a planet from forming where the asteroid belt now exists, its gravitational tugs disrupting the orbits of debris before they could coalesce into a single world. Some scientists believe that Jupiter played an even more dramatic role in shaping the inner solar system. According to the Grand Tack hypothesis, Jupiter may have migrated inward during the early solar system, approaching as close as the present orbit of Mars before reversing course and moving back outward. This migration would have swept through the region where the rocky planets were forming, scattering debris and potentially delivering water and organic compounds to the young Earth. Whether or not the Grand Tack occurred exactly as proposed, there is little doubt that Jupiter's influence has been profound. Its gravity creates resonances that shape the orbits of asteroids and comets. It deflects some incoming objects away from the inner solar system, while redirecting others toward us. Some researchers have suggested that Jupiter acts as a cosmic shield, protecting Earth from asteroid impacts, while others argue that it just as often sends dangerous objects our way. The truth is probably somewhere in between. Jupiter's influence on the population of impacting bodies is complex and has changed over time. In the early solar system, it may have increased the bombardment rate by stirring up material that might otherwise have settled into stable orbits. Today, it probably does deflect some comets that might otherwise reach the inner planets. The overall effect has been to shape the environment in which life on Earth has evolved, for better and for worse. Jupiter's moons also owe their existence and their nature to the giant planet's gravitational dominance. The 4 largest moons, known as the Galilean moons because Galileo discovered them in 1610, are worlds in their own right. Each has a unique character and a complex relationship with the planet it orbits. Io, the innermost of the 4, is the most volcanically active body in the solar system. Its surface is constantly renewed by eruptions that spray sulfur and silicate lava across the landscape. This volcanic activity is driven by tidal heating, the result of Jupiter's immense gravity flexing Io's interior as the Moon moves through its orbit. The heat generated by this flexing melts rock within Io, creating the magma that feeds its volcanoes. Europa, the next moon out, is covered in a smooth shell of ice. But beneath that ice lies a global ocean of liquid water, kept warm by the same tidal heating that powers Io's volcanoes. This ocean has made Europa one of the most promising places to search for life beyond Earth. The ingredients for life may all be present: liquid water, chemical energy from rock-water reactions, and the complex organic molecules that pervade the solar system. Ganymede is, as the largest moon in the solar system, bigger even than the planet Mercury. It has its own magnetic field, the only moon known to possess one, generated by an iron core similar to Earth's. Ganymede's surface shows evidence of both ancient heavily cratered terrain and younger regions reshaped by geological activity. Like Europa, it may harbour a subsurface ocean, though buried deeper beneath the ice. Callisto, the outermost of the Galilean moons, is a frozen world covered in craters. It lacks the internal heat that drives geological activity on the other large moons, so its surface has remained largely unchanged for billions of years. Callisto is like a museum of the ancient solar system, preserving a record of impacts that other worlds have long since erased. Beyond the Galilean moons, Jupiter has dozens of smaller satellites with more chaotic histories. Popwam. Many of these are captured asteroids, objects that wandered too close to Jupiter and were snared by its gravity. They orbit in irregular patterns, some moving backward compared to the planet's rotation, others tilted at steep angles to the equatorial plane. These captured moons come in families, clusters of objects with similar orbits that probably originated from the breakup of larger parent bodies. When asteroids were captured into orbit around Jupiter, some of them were eventually shattered by impacts with other debris. The fragments remained in similar orbits, creating the families we observe today. Jupiter's gravity continues to capture new objects from time to time. In 1994, the comet Shoemaker-Levy 9 provided a dramatic demonstration of this process. The comet had been captured into orbit around Jupiter years earlier, and tidal forces from the planet had torn it into a chain of fragments. In July of 1994, those fragments slammed into Jupiter's atmosphere one by one, creating dark impact scars that were visible for months. The impacts were the first collision between solar system bodies ever observed in real time. Telescopes around the world and in orbit watched as each fragment struck, creating fireballs that rose thousands of miles above the cloud tops before falling back. The energy released was enormous, equivalent to hundreds of millions of nuclear weapons. Jupiter absorbed the blows without lasting damage, its immense bulk easily absorbing the energy of the impacts. Shoemaker-Levy 9 reminded us that the solar system is a dynamic place where collisions still occur. Jupiter's gravity makes it a particularly effective attractor for stray bodies, sweeping up debris that might otherwise wander through the inner solar system. The planet bears the scars of countless ancient impacts, though most have long since faded into the churning atmosphere. Juno has not focused primarily on Jupiter's moons, but it has made close passes by several of them during its extended mission. The spacecraft has observed Ganymede, Europa, and Io from distances that allowed detailed imaging and scientific measurements. These flybys have provided valuable data complementing what we learned from earlier missions like Galileo. The Juno observations of Io revealed new details about the moon's volcanic activity. The spacecraft captured images of volcanic plumes rising from the surface and detected the heat signatures of active eruptions. It also studied how material from Io's volcanoes spreads through Jupiter's magnetic field, feeding the plasma torus that helps power the auroras. The close pass by Europa offered tantalizing glimpses of that ocean world's icy surface. Phaenas, Juno's instruments measured the thickness of Europa's ice shell and searched for signs of water vapor or other materials escaping into space. Every bit of data about Europa is valuable, since the moon is a prime target for future missions seeking signs of life in its hidden ocean. Ganymede received particular attention during Juno's flyby, the closest approach to that giant moon in over 2 decades. The spacecraft mapped Ganymede's magnetic field in detail, studied its thin atmosphere, and captured high-resolution images of its cratered and grooved surface. The data revealed new features and helped scientists understand how Ganymede's magnetic field interacts with the larger magnetic field of Jupiter. The study of Jupiter's moons connects directly to our understanding of the planet itself. The moons formed from the same disk of material that surrounded Jupiter in its youth, and their compositions tell us about the conditions in that disk. The tidal interactions between Jupiter and its moons generate heat and drive geological activity that would not exist without the planet's massive gravity. Jupiter and its moons form a miniature solar system in their own right, a laboratory for understanding how planetary systems work. The dynamics of this system have been studied for centuries, beginning with Galileo's first observations and continuing through the detailed measurements made by modern spacecraft. Each new observation reveals additional complexity and raises new questions about how this remarkable system came to be. Let us return now to Juno and consider what lies ahead for the mission and for our understanding of Jupiter. The spacecraft has already far exceeded its original goals, continuing to operate years after it was expected to fail. But even Juno's remarkable instruments can only scratch the surface of the mysteries that Jupiter holds. Juno's orbit is slowly changing, affected by the gravitational perturbations of Jupiter's moons and the planet's own asymmetric mass distribution. The spacecraft's perigeo, the closest point in its orbit, has been gradually moving northward, allowing it to study different regions of the planet's atmosphere over time. This orbital evolution was anticipated by mission planners and has allowed Juno to map a larger fraction of Jupiter's surface than would otherwise be possible. The mission has been extended multiple times, taking advantage of the spacecraft's continued health to gather additional data. Each orbit brings new opportunities to observe the planet's weather, measure its magnetic field, and peer beneath its clouds. The extended mission has also allowed Juno to make those close flybys of the Galilean moons, adding an important dimension to its scientific return. Eventually, Juno will meet the same fate as many spacecraft that have explored the outer planets. When its fuel runs low or its instruments finally fail, it will be commanded to dive into Jupiter's atmosphere, ensuring that it does not accidentally contaminate the potentially habitable moons Europa or Ganymede. The spacecraft will burn up as it descends, destroyed by the same crushing pressures and rising temperatures that we have been imagining throughout our journey. But Juno's legacy will continue long after the spacecraft is gone. The data it has gathered will be analyzed for years, perhaps decades, as scientists work to understand all the implications of its discoveries. New theories will be proposed and tested against Juno's measurements. And the questions that Juno could not answer will help guide the design of future missions to the giant planets. Those future missions are already being planned. The European Space Agency's JUICE mission, which launched in 2023, is en route to Jupiter now. It will arrive in 2031 and focus primarily on Ganymede, eventually becoming the first spacecraft to orbit a moon other than Earth's. Along the way, it will make flybys of Europa and Callisto, adding to our knowledge of those worlds. NASA's Europa Clipper mission is also underway, with plans to study Europa in unprecedented detail. Rather than orbiting Europa directly, which would expose the spacecraft to intense radiation from Jupiter's magnetic field, Europa Clipper will make dozens of close flybys while orbiting Jupiter. Each flyby will allow the spacecraft to study a different region of Europa's surface and probe the ocean beneath. These missions will build on what Juno has taught us, using that knowledge to ask deeper questions about Jupiter and its moons. The giant planet remains a world of mysteries, its depths largely unexplored, and its history only partially understood. Each generation of spacecraft reveals new wonders and raises new puzzles that inspire the next generation of exploration. For now, let us drift away from Jupiter and consider what we have learned on our imaginary journey. We have descended through clouds of ammonia and ammonium hydrosulfide, sinking through an atmosphere that grows ever denser with depth. We have passed through the layer where liquid hydrogen fills an ocean without shores, and continued down to where that hydrogen transforms into an exotic metallic state. We have seen storms that dwarf our entire planet, hurricanes that rage for centuries, and cyclones arranged in geometric patterns at the poles. We have traced the magnetic field lines that link Jupiter to its volcanic moon Io and power auroras of stunning brightness and complexity. And we have glimpsed the fuzzy core at the planet's heart, where heavy elements mix with hydrogen in a primordial blend shaped by ancient collisions. Jupiter is a world of extremes in every dimension. Its size, its magnetic field, its internal heat, its gravitational influence, all are the largest in the solar system outside the Sun itself. To study Jupiter is to push our understanding of physics and chemistry to their limits, exploring conditions that cannot be replicated in any laboratory on Earth. And yet, for all its strangeness, Jupiter is connected to us in profound ways. The planet formed from the same cloud of gas and dust that gave birth to the Sun and Earth. Its gravity has shaped the architecture of the solar system, influencing which asteroids and comets eventually reached our world. The heavy elements in its atmosphere were forged in ancient stars and scattered through space by supernova explosions, the same elements that make up our bodies and our planet. When we study Jupiter, we are studying our own origins. We are reaching back across 4.6 billion years to understand the processes that shape the solar system we call home. We are asking questions about how planets form, how they evolve, and what makes each world unique. And we are preparing ourselves for the discovery of countless other Jupiters around other stars, worlds that may teach us still more about the nature of giant planets. The universe is full of Jupiters. In the years since the first exoplanet was discovered in 1995, astronomers have found thousands of giant planets orbiting other stars. Many of them are similar to Jupiter in size and mass, though they exist in a bewildering variety of orbits. Some orbit so close to their stars that their atmospheres are heated to thousands of degrees. Others drift through the cold outer reaches of their solar systems, in positions similar to where we find our own Jupiter. These exojupiters cannot be studied in the same detail as our Jupiter. They are too far away to visit with spacecraft, and even the best telescopes can only reveal hints of their nature. But they can be studied through their effects on their parent stars and through the light that filters through their atmospheres during transits. And everything we learn about our own Jupiter helps us interpret those distant observations. When astronomers detect water vapor in the atmosphere of a distant gas giant, they understand what that means because we have studied water in Jupiter's atmosphere. When they measure the magnetic field of an exoplanet through its effects on its star, they can interpret that measurement because we have mapped Jupiter's magnetic field in detail. Our solar system serves as a Rosetta Stone for understanding the wider universe, and Jupiter is one of the most important chapters in that reference. So as you drift towards sleep tonight, carry with you the image of that giant world spinning in the darkness. Think of the storms raging across its surface, storms that have outlasted human civilizations and will continue long after we are gone. Think of the patient spacecraft circling above, gathering data that will shape our understanding for generations. Think of the mysteries still hidden beneath those beautiful bands of cloud, secrets that future missions may one day reveal. Jupiter has been watching over the solar system for 4.5 billion years. It witnessed the formation of Earth and the late heavy bombardment that scarred our moon. It watched as life emerged from the primordial oceans and spread across our planet's surface. It continues to turn through its 10-hour days and 12-year orbits, indifferent to the affairs of the small world where we make our home. And yet, on that small world, curious minds have built instruments capable of unveiling the giant secrets. We have sent our machines across 1 billion miles of space to study a world we can never visit in person. We have peered beneath clouds no human eye can penetrate and mapped the invisible forces that shape the planet's interior. We have begun to understand our neighbor, even if that understanding remains incomplete. That is the nature of science, an endless journey toward understanding, each discovery revealing new horizons to explore. Jupiter will continue to surprise us as we develop new technologies and ask new questions. The planet that inspired awe in our ancestors will inspire equal awe in our descendants, who may know its secrets far better than we do today. For now, let the thought of that immense world be a comfort. The universe is vast and old and full of wonders we are only beginning to comprehend. We are small, but we are capable of great things. We have reached across the darkness to touch the face of a giant, and in doing so, we have learned something precious about our own place in the cosmos. The storms of Jupiter continue to rage. The magnetic field continues to pulse with invisible power. The metallic hydrogen continues to flow in the eternal darkness far below. And far above, a small spacecraft, named for a goddess who could see through clouds, continues its patient work, watching, measuring, revealing. Sleep now, and let your mind drift among the stars. Tomorrow, the universe will still be there, patient and mysterious, waiting for us to ask our next questions. But tonight, let the wonders we have contemplated carry you into peaceful rest. The giant planet turns through the night, and somewhere in the darkness, secrets billions of years old are slowly coming to light. Let us continue our exploration now, descending once more into the scientific details that make Jupiter such a fascinating subject of study. The more we learn about this planet, the more we realize how much remains unknown. Each answer seems to raise new questions. Each discovery opens new avenues of investigation. Consider the question of Jupiter's formation, which has puzzled scientists for decades. The traditional model, known as core accretion, suggests that Jupiter began as a rocky core not unlike the other planets in the inner solar system. This core grew by accumulating solid material from the surrounding disk, gradually building up mass until it reached a critical threshold. At that point, its gravity became strong enough to capture gas directly from the nebula, and the planet grew rapidly to its present size. This model makes intuitive sense and has been successful in explaining many features of Jupiter and other giant planets. But it has problems as well. Chief among these is the timescale required for the rocky core to grow large enough. The gas in the nebula does not last forever. It disperses into space within just a few million years after a star forms. For core accretion to work, the rocky core must reach critical mass before the gas disappears. Early calculations suggested this was difficult to achieve, especially at Jupiter's distance from the Sun, where solid material is more spread out. The core would need to grow very quickly, accumulating material faster than seemed physically possible. This led some scientists to propose alternative formation mechanisms, including the idea that Jupiter formed through direct gravitational collapse of a dense region in the nebula, similar to how stars form. More recent calculations have been more favorable to core accretion, taking into account factors that were neglected in earlier work, the presence of small pebbles in the disk, rather than only larger planetesimals, can greatly accelerate core growth. Pebble accretion, as this process is called, allows a forming planet to sweep up material much more efficiently than if it had to rely on collisions with larger objects. Juno's measurements have added important constraints to these formation models. The enrichment of heavy elements in Jupiter's atmosphere tells us something about what the planet accumulated as it formed. If Jupiter had formed purely through gravitational collapse of gas, it would have a composition similar to the Sun. The fact that it is enriched in heavy elements shows that solid material played an important role in its formation. The diffuse nature of Jupiter's core also provides clues about its early history. A compact rocky core would suggest relatively gentle formation, with solid material accumulating at the center and staying there. The fuzzy, dilute core that Juno has detected suggests a more turbulent history, perhaps including the giant impact we mentioned earlier that mixed the core material with the surrounding hydrogen. Some of the most exciting research on Jupiter's formation involves comparison with other giant planets, both in our solar system and around other stars. Saturn, Uranus, and Neptune each formed through similar processes, but ended up with very different results. Saturn is similar to Jupiter, but smaller and less dense. Uranus and Neptune are ice giants rather than gas giants, with much higher proportions of water and other heavy materials. These differences reflect the conditions in different parts of the early solar system. Jupiter formed close enough to the Sun that water ice was not abundant in its vicinity. Saturn formed farther out, where ice was more common, but it did not grow quite as large as Jupiter before the nebula dispersed. Uranus and Neptune formed even farther out, where growth was slower, and they never captured as much gas. The exoplanet discoveries have shown us even greater diversity. Hot Jupiters, giant planets orbiting very close to their stars, cannot have formed where we find them. The disk would have been too hot for solid material to exist. They must have migrated inward from farther out, raising questions about what stopped our own Jupiter from migrating all the way into the inner solar system. The answers to these questions are still being debated, but Jupiter's composition and structure provide essential data for testing different theories. Every measurement Juno makes adds another piece to the puzzle, constraining what is possible and ruling out scenarios that do not match the observations. One area where Juno has been particularly valuable is in understanding Jupiter's interior structure in 3 dimensions. Earlier missions could observe the planet only from certain angles and at certain times. Juno's polar orbit allows it to pass over every part of the planet eventually, building up a complete map of the magnetic field and gravitational anomalies. These maps have revealed asymmetries that were not apparent before. Jupiter's northern and southern hemispheres are not mirror images of each other. There are differences in the structure and intensity of the magnetic field between the 2 poles. The winds and weather patterns also show north-south asymmetries that are not yet fully understood. Some of these asymmetries may be related to the planet's internal structure. If the core is not perfectly centered, or if there are density variations deep within the planet, they would affect the gravitational field and possibly the magnetic field as well. The detailed maps from Juno allow scientists to probe these deep structures, even though no instrument can directly observe them. The behavior of Jupiter's atmosphere provides another window into the planet's interior. Atmospheric dynamics are driven by the interplay between rotation, internal heat, and solar heating. By understanding how the atmosphere moves and how storms form and evolve, scientists can infer something about the conditions deeper down. One of the key questions is how energy is transported from the deep interior to the outer atmosphere. Jupiter radiates about 1.7 times as much energy as it receives from the Sun, and that excess energy must come from the planet's interior. Some of it is primordial heat left over from formation, slowly leaking out through the atmosphere over billions of years. Some of it is generated by ongoing contraction as the planet slowly shrinks under its own gravity. This energy flows outward through the atmosphere by convection, the same process that moves hot air upward and cold air downward on Earth. But Jupiter's convection is complicated by the planet's rapid rotation, which tends to organize the flow into columns aligned with the rotation axis. The interplay between convection and rotation creates the banded structure we observe, with winds blowing in opposite directions in alternating zones and belts. Juno's observations have helped clarify how deep this banded structure extends and what happens at the boundary where the winds die out. Below about 1,800 miles, the atmosphere transitions to a more uniform state, probably because the electrical conductivity of the material increases enough that the magnetic field becomes important in organizing the flow. This transition zone is a key boundary in Jupiter's interior structure. Above it, the atmosphere is electrically insulating and can flow relatively freely in bands and vortices. Below it, the increasing conductivity couples the flow to the magnetic field, and different dynamics take over. The exact depth of this transition, which Juno has measured, tells us about the electrical properties of hydrogen under extreme pressure. The winds in Jupiter's atmosphere are among the strongest in the solar system. Jet streams at the boundaries between zones and belts blow at several hundred miles per hour, far faster than any winds on Earth. These jets have remained stable for as long as we have observed them, maintaining their positions and speeds decade after decade. The stability of Jupiter's jets is remarkable given the turbulent nature of the atmosphere. Storms constantly form and dissipate, merging and splitting as they interact with each other and with the background flow. On Earth, such turbulence would quickly disrupt any organized pattern. On Jupiter, the combination of rapid rotation and the lack of a solid surface allows the jets to persist indefinitely. Numerical simulations have helped scientists understand why this is. The key is that Jupiter's atmosphere is thick enough that vertical motions are strongly suppressed in certain regions, forcing the flow to organize into horizontal patterns. The energy from storms and convection pumps into the jets rather than disrupting them, a process called inverse cascade that concentrates energy at large scales rather than dissipating it at small scales. These same processes are believed to operate in the atmospheres of stars and in Earth's oceans, making Jupiter a valuable laboratory for studying a type of fluid dynamics that is difficult to explore under controlled conditions. The planet provides a natural experiment on a scale no human facility could match. The colors of Jupiter's atmosphere add another dimension to the mystery. We see browns, oranges, reds, and whites in the clouds, with different colors appearing in different regions and at different times. The chemicals responsible for these colors have been debated for decades, and we still do not have a definitive answer. The white zones are relatively straightforward. They are probably clouds of ammonia ice, similar to the cirrus clouds of water ice high in Earth's atmosphere. The ammonia condenses out of the rising air in these regions, forming bright white crystals that reflect sunlight. The darker belts are more mysterious. The brown and tan colors suggest the presence of compounds that absorb blue light, but the exact identity of those compounds is uncertain. Sulfur and phosphorus compounds have been proposed, as have various organic molecules created by photochemical reactions in the upper atmosphere. The red color of the Great Red Spot is perhaps the most iconic feature of Jupiter's appearance, and its origin has been particularly puzzling. The spot has varied in color over the years, sometimes appearing more orange or brown rather than red. This variability suggests that the color is not intrinsic to the materials in the storm, but depends on conditions like altitude, solar exposure, and chemical processing. Recent laboratory experiments have suggested that the red color may come from photochemical processing of ammonia and acetylene, two compounds known to exist in Jupiter's upper atmosphere. When exposed to ultraviolet light, these molecules can combine to form complex organic compounds with reddish-brown colors. The Great Red Spot rises higher into the atmosphere than surrounding clouds, exposing its materials to more intense solar radiation and promoting this photochemical reddening. These colored compounds are probably present only in thin coatings on the actual cloud particles, which are still mostly ammonia ice. A tiny amount of colored material can give a dramatic tint to the clouds, while representing only a small fraction of the total mass. This explains why the colors can change relatively quickly as conditions in the atmosphere shift. Understanding Jupiter's colors matters because it tells us about the chemistry occurring in the atmosphere. The molecules that form as products of photochemical reactions can affect the thermal balance of the atmosphere, absorbing sunlight and re-radiating it as heat. They may also play roles in other chemical processes that we do not yet fully understand. The distribution of colors also provides clues about atmospheric circulation. If a region appears darker, it may indicate downwelling air that brings colored compounds from higher altitudes, or it may indicate clearer air that allows us to see deeper into the atmosphere where different chemicals exist. Mapping the colors in detail helps scientists trace the three-dimensional flow patterns that move material around the planet. Juno has contributed to color studies by observing Jupiter at wavelengths beyond the visible range. Infrared observations reveal the heat signatures of different atmospheric layers, showing which regions are warmer or cooler. Ultraviolet observations detect the hazes of photochemical products high in the atmosphere. Together with visible light images, these data help construct a comprehensive picture of atmospheric structure and composition. One of the most striking sets of images Juno has returned are the close-up views of Jupiter's cloud tops during perijove passes. These images reveal a wealth of detail invisible from Earth or from spacecraft at greater distances. Small-scale features like pops, white bright spots that may be convective storms punching through from below, dot the landscape of the cloud deck. The complexity of these small-scale features was unexpected. Scientists had assumed that Jupiter's rapid rotation and thick atmosphere would smooth out small structures, leaving only the large-scale bands and major storms visible. Instead, Juno revealed an almost fractal complexity, with structure apparent at every scale the cameras could resolve. Some of these features resemble weather patterns on Earth, like the spiral arms of hurricanes, or the cellular patterns of convection in heated fluids. Others are unlike anything we see on our home planet, reflecting the alien conditions of Jupiter's atmosphere. The variety is endless, and each perijove pass reveals new examples. The images have also captured moments of atmospheric drama, like the merging of storms or the birth of new vortices. These events happen slowly by human standards, playing out over days or weeks. But Juno's repeated passes allow scientists to track their evolution over time. Animation sequences created from Juno images show the atmosphere in constant motion, churning and flowing like a living thing. Amateur astronomers have made important contributions to this work. Ground-based observers around the world monitor Jupiter continuously, tracking changes in its appearance between Juno's relatively infrequent close passes. When a new feature appears or an existing storm undergoes a transformation, amateur reports often provide the first alert. The professional scientists then know to look for those changes in Juno's data. This collaboration between professional and amateur communities reflects the democratic nature of planetary science. Jupiter is visible to anyone with a small telescope, and its changing appearance invites continuous observation. The contributions of amateur astronomers extend the baseline of coverage and catch transient events that might otherwise be missed. Let us now consider some of the smaller-scale features that Juno has revealed, starting with the remarkable diversity of vortices in Jupiter's atmosphere. We have already discussed the Great Red Spot and the polar cyclones, but the planet hosts countless other rotating storms of various sizes and colors. White ovals are anticyclonic storms, rotating in the opposite direction from the Great Red Spot. Several prominent white ovals have been tracked for decades, and some have merged together over time. In 1998 and 2000, 3 white ovals that had existed since the 1930s merged into a single larger storm called Oval BA. This storm has sometimes taken on a reddish color, earning it the nickname Little Red Spot. The merging of these storms demonstrates that Jupiter's atmosphere is not static, but evolving over human timescales. The storms interact with each other and with the background flow, sometimes combining and sometimes tearing each other apart. Predicting these interactions is difficult because the underlying physics is chaotic, sensitive to small changes in initial conditions. Brown barges are elongated dark features that appear in the belts of Jupiter's atmosphere. They are probably regions of relatively clear air where we can see deeper into the atmosphere, rather than distinct storm systems. The darker color may come from the different chemical composition at greater depths, or from the absence of the bright ammonia ice clouds that cover shallower regions. Festoons are dark streamers that extend from the belts into the adjacent zones, suggesting the presence of winds or waves that carry material across the band boundaries. They add to the visual complexity of Jupiter's appearance and provide evidence for atmospheric dynamics that cross the neat pattern of alternating zones and belts. Hotspots are regions where the upper atmosphere is unusually clear, allowing infrared radiation from deeper, warmer layers to escape into space. These were first detected by ground-based observations and have been studied by several spacecraft. The Galileo probe descended into one of these hotspots, which is why it measured lower water abundances than expected. Hotspots are apparently dry regions where water-bearing clouds have been suppressed. Juno's microwave observations have helped map the three-dimensional structure of hotspots, showing how they extend down through the atmosphere. They appear to be places where air is descending, suppressing cloud formation and creating windows to greater depths. The pattern of hotspots around Jupiter correlates with features in the cloud structure, confirming their connection to larger atmospheric circulation patterns. Pop-up clouds, visible in some of Juno's highest resolution images, are small, bright features that appear to punch up through the surrounding cloud deck. These may be the tops of vigorous convective storms, places where air is rising rapidly enough to carry cloud material to unusually high altitudes. They are the Jovian equivalent of the towering cumulonimbus clouds that produce thunderstorms on Earth. The ubiquity of these features suggests that convection is occurring throughout Jupiter's atmosphere, not just in certain regions or under certain conditions. The heat flowing up from the interior keeps the atmosphere in a state of continuous churning, with rising and sinking motions at scales from small to enormous. Now let us turn our attention to a topic we touched on earlier: the interactions between Jupiter and its moons, particularly the volcanic satellite Io. These interactions create some of the most dramatic phenomena in the Jovian system, and have taught us much about how giant planets and their satellites influence each other. Io orbits Jupiter at a distance of about 262,000 miles, completing one orbit every 1.77 Earth days. This may sound like a comfortable distance, but in astronomical terms, Io is very close to its parent planet. Jupiter looms enormous in Io's sky, and the planet's gravity raises tidal bulges on the Moon many times larger than the tides the Moon raises on Earth. What makes Io's situation particularly interesting is its orbital resonance with the other Galilean moons. Io, Europa, and Ganymede are locked in a pattern called a Laplace resonance, where their orbital periods have the ratio 1.2.4. For every orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This resonance prevents the orbits from becoming perfectly circular. Europa and Ganymede continually give Io tiny gravitational tugs at the same points in its orbit, forcing it to maintain a slightly elliptical path. As Io moves closer to and farther from Jupiter in this elliptical orbit, the strength of Jupiter's tidal force varies, and the tidal bulge on Io grows and shrinks. This constant flexing of Io's interior generates enormous amounts of heat. The rock inside the moon is squeezed and stretched with every orbit, and the friction from this deformation produces enough thermal energy to melt rock. The result is the spectacular volcanic activity we observe, with hundreds of active volcanoes continuously reshaping Io's surface. The volcanic eruptions on Io spray material into space at such high velocities that some of it escapes the moon's weak gravity entirely. This material spreads along Io's orbit, creating a donut-shaped ring of plasma called the Io torus. The plasma consists mainly of sulfur and oxygen ions, products of Io's sulfur-rich volcanism. Jupiter's magnetic field sweeps through the Io torus, accelerating particles and creating electrical currents that flow along the field lines. Some of these currents connect Io directly to Jupiter's atmosphere, forming what is called the Io flux tube. The energy dissipated in this flux tube heats the atmosphere and creates the bright auroral spot at Io's magnetic footprint. The amount of power flowing through the Io flux tube is staggering, equivalent to hundreds of millions of watts. This electrical connection between moon and planet is unique in the solar system, a circuit that spans hundreds of thousands of miles and has been operating for billions of years. Juno has studied the Io flux tube in detail, measuring the particles and fields along its length. The spacecraft has also observed the Io footprint auroras, bright spots that move across Jupiter's polar regions as Io orbits. These observations help scientists understand the complex physics of this electromagnetic interaction. The other Galilean moons also create flux tubes and auroral footprints, though none as dramatic as Io's. Europa's footprint is visible, but fainter, powered by the smaller amount of plasma generated by that moon. Ganymede's footprint is complicated by the moon's own magnetic field, which creates a barrier around it that partially blocks the connection to Jupiter. The mass loading from the Io torus affects Jupiter's magnetosphere in important ways. The constant injection of new plasma causes the magnetosphere to inflate outward, extending it to greater distances than it would reach otherwise. The plasma also drives various waves and instabilities that propagate through the magnetosphere, creating a dynamic environment quite different from the more stable magnetosphere of Earth. Jupiter's magnetosphere is so large that it would appear larger than the full moon in Earth's sky if we could see it. It extends several million miles in the sunward direction and is blown back by the solar wind into a long tail that may reach past the orbit of Saturn. When the Cassini spacecraft flew past Jupiter in 2000 on its way to Saturn, it detected the effects of Jupiter's magnetosphere from enormous distances. The radiation belts within this magnetosphere are the most intense in the solar system. Charged particles are trapped by the magnetic field and accelerated to tremendous energies, creating zones of radiation that would be deadly to any human or electronic system that entered them. The inner radiation belts, close to Jupiter, are particularly harsh. Juno's orbit was designed specifically to minimize exposure to these radiation belts. By approaching Jupiter over the poles, rather than over the equator, the spacecraft avoids the most intense regions. Even so, Juno carries heavy radiation shielding around its sensitive electronics, a vault of titanium that protects the instruments from the energetic particles. Despite this shielding, Juno has experienced some radiation damage over its years of operation. This is expected and was planned for. The original mission was designed to last only about 2 years, with the understanding that radiation would eventually degrade the spacecraft systems. The fact that Juno has continued operating for so much longer is a testament to the durability of its design and the skill of its operators. The radiation environment at Jupiter poses challenges for future exploration of the Galilean moons. Europa Clipper and JUICE will both need robust radiation protection to survive their missions. Long-term habitation or detailed surface exploration of Europa or any of the inner moons would require even more advanced shielding technology than we currently possess. Let us pause for a moment in our exploration and reflect on what we have learned. We have traveled from the visible cloud tops down through thousands of miles of increasingly compressed atmosphere. We have seen storms that dwarf our planet and magnetic fields that span the solar system. We have visited the moons that orbit this giant world and observed the violent interactions between Io's volcanism and Jupiter's magnetosphere. Each layer of Jupiter holds its own mysteries, and each mystery connects to larger questions about how planets form and evolve. The deep interior reveals conditions present in the early solar system. The atmosphere demonstrates fluid dynamics under conditions impossible to replicate on Earth. The moons and magnetosphere show how a giant planet can influence its entire surroundings. And all of this is being revealed by instruments and spacecraft built by human hands, designed by human minds, operated by teams of dedicated scientists and engineers. We cannot visit Jupiter in person, and perhaps we never will. But through our machines, we have extended our senses across 1 billion miles of space and begun to comprehend a world utterly unlike our own. This is the power of science and exploration. We are small creatures on a small planet, living brief lives in a cosmos that spans billions of years. But we have found ways to reach beyond our limitations, to see things no eye has ever seen, to know things no mind has ever known before. Jupiter has been shining in our sky since before humans existed, but only in this generation have we begun to truly understand it. The journey is far from over. Future missions will build on Juno's discoveries, probing deeper into Jupiter's secrets and exploring its moons in greater detail. New instruments and techniques will reveal aspects of the planet that we cannot even imagine today. And perhaps, someday, humans themselves will venture to the Jovian system, seeing with their own eyes what their robotic predecessors have shown them. For now, let us continue our imaginary voyage, returning to some topics we have touched on only briefly and exploring them in greater depth. The scientific richness of Jupiter is inexhaustible, and every aspect rewards careful attention. Consider, for example, the dynamics of the atmospheric bands in more detail. We have mentioned that Jupiter's zones and belts are driven by a combination of rotation and convection, but the exact mechanisms remain subjects of active research. Why do the bands have the widths they do? Why do the jets blow at particular speeds? What determines where storms form and how long they last? Part of the answer lies in the concept of Rossby waves, large-scale undulations in the flow that are influenced by the planet's rotation. On Earth, Rossby waves are responsible for the meandering jet stream that brings weather systems across the middle latitudes. On Jupiter, similar waves help organize the banded structure, creating the alternating eastward and westward jets that define the zones and belts. The widths of the bands are related to a quantity called the Rossby deformation radius, which depends on the rotation rate of the planet and the temperature structure of the atmosphere. On Jupiter, this radius works out to values that match the observed band widths reasonably well. The theory explains why the bands are broader near the equator and narrower toward the poles, a pattern that is clearly visible in images. but the details are still being worked out. The theory predicts average properties, not the specific structures we observe in any given image. Juno's data are helping to test and refine these theories, providing measurements of wind speeds and temperatures at different depths that were previously unavailable. The transition between the banded upper atmosphere and the more uniform deep interior is another area where Juno has made important contributions. We mentioned that this transition occurs at about 1,800 miles depth, but the exact nature of the boundary is still uncertain. Is it a sharp transition or a gradual one? How do the winds decrease with depth? What role does the magnetic field play? The answers depend on the electrical conductivity of the material at different depths. In the upper atmosphere, hydrogen behaves as an insulator, and the magnetic field has little effect on the flow. Deeper down, the increasing pressure ionizes the hydrogen, making it electrically conductive. Once conductivity reaches a certain level, the magnetic field begins to break the winds, gradually bringing them to a halt. This magnetic braking explains why the banded structure does not extend to arbitrary depths. Below the transition zone, the coupling between the magnetic field and the flow prevents the organized bands from maintaining themselves. The atmosphere becomes more sluggish, flowing slowly in response to the thermal and magnetic forces acting on it. Juno's combined measurements of gravity and magnetism have allowed scientists to study this transition in detail. The gravity data show where the density variations associated with the bands disappear. The magnetic data show where the field becomes strong enough to affect the flow. Together, they provide a consistent picture of how the two regimes connect. The implications extend beyond Jupiter to other giant planets. Saturn, Uranus, and Neptune also have banded atmospheres, and similar principles probably govern their transitions to deeper layers. The Cassini mission studied Saturn's atmosphere in detail, finding both similarities to and differences from Jupiter. Uranus and Neptune remain less well understood, awaiting future missions that can study them as closely as Juno has studied Jupiter. The exoplanets discovered around other stars present an even greater diversity of giant planet atmospheres. Hot Jupiters, with their extreme temperatures and possibly tidally locked rotations, may have very different wind patterns and banded structures than anything in our solar system. Observations of their atmospheres are beginning to reveal some of these differences. Though our understanding remains limited, Jupiter serves as the template against which all other giant planets are compared. It is the most accessible giant planet for detailed study, and the theories developed to explain its behavior form the foundation for understanding more distant worlds. Every measurement Juno makes has implications not just for Jupiter, but for planetary science as a whole. Now let us turn to a topic that has fascinated observers for centuries: the rotation of Jupiter and the patterns it creates in the atmosphere. We have mentioned that Jupiter rotates quickly, completing one rotation in just under 10 hours. But defining exactly how fast Jupiter rotates turns out to be surprisingly complicated. Unlike Earth, which has a solid surface whose motion defines the planet's rotation rate, Jupiter has no fixed landmarks. The clouds we observe move at different speeds depending on their latitude, with equatorial clouds racing ahead of those at higher latitudes. Which of these cloud bands, if any, represents the true rotation of the planet? For many years, scientists used radio emissions from Jupiter's magnetosphere to define the rotation rate. The magnetic field is anchored in the deep interior, and the radio signals it generates come around at regular intervals as the planet rotates. The period measured from these radio bursts was adopted as the standard rotation period of Jupiter: 9 hours, 55 minutes, and 29.7 seconds. But this value turned out to be slightly wrong. The radio emissions come from the magnetic field, and the magnetic field is generated in the metallic hydrogen layer, which may not rotate at exactly the same rate as the deeper interior. Juno's gravity measurements have provided a more accurate measure of the interior rotation, and the new value differs from the old one by a few seconds. This may seem like a trivial difference, but it matters for understanding Jupiter's structure and dynamics. The rotation rate affects calculations of wind speeds, which are measured relative to the interior. It also affects models of the planet's internal structure, which depend on knowing exactly how fast the mass is spinning. The wind speeds in Jupiter's atmosphere are truly impressive. At the equator, the clouds race around the planet at about 250 miles per hour relative to the deep interior. This is faster than any hurricane on Earth, and it extends completely around the planet's equator. The equatorial jet is by far the strongest and most stable wind system on Jupiter. At higher latitudes, alternating jets blow eastward and westward, creating the pattern of zones and belts we observe. These jets range in speed from a few tens to a few hundred miles per hour. With the eastward jets generally stronger than the westward ones, the pattern is roughly symmetric between the northern and southern hemispheres, though there are some differences. Jet streams on Earth are driven primarily by temperature differences between the equator and poles, ultimately powered by differential solar heating. Jupiter's jets have a different origin. The Sun provides some heating, but the more important energy source is the internal heat flowing up from the planet's core. This creates convective cells that pump energy into the jets through the inverse cascade process we mentioned earlier. The stability of Jupiter's jets over centuries of observation is remarkable. Individual storms come and go, but the underlying pattern of alternating jets remains constant. This suggests that the jets represent a fundamental state of the atmosphere, determined by the planet's rotation rate and internal heat flow, rather than by transient weather events. Some theoretical models suggest that the jets might oscillate between different states over very long timescales, with the pattern of eastward and westward winds reversing periodically. There is no observational evidence for this, but our record of Jupiter observations spans only a few centuries at best. The planet has been rotating for billions of years, and changes that seem slow to us might be rapid on geological timescales. One feature that does seem to be changing on human timescales is the Great Red Spot. We have mentioned that this iconic storm has been shrinking over the past century or so. Historical records suggest the spot was once significantly larger than it is today, perhaps twice its current width. If the shrinking continues at its recent rate, the Great Red Spot could become roughly circular rather than oval within a few decades. Whether the storm will eventually disappear entirely is unknown. Some scientists have predicted its demise, extrapolating the current trend into the future. Others point out that the spot has survived for centuries despite constant changes in its size and shape, and argue that it may be more resilient than simple extrapolation suggests. The Great Red Spot may be sustained by interactions with smaller storms that occasionally collide with it. These collisions sometimes seem to inject energy into the spot, causing temporary changes in its rotation speed or color. A recent series of such collisions caused flakes of red material to tear away from the spot's edge, creating dramatic images that some observers initially interpreted as the storm tearing itself apart. In fact, the spot recovered from these apparent wounds without lasting damage. The flakes of material were reabsorbed or dispersed, and, the storm continued spinning as before. Such resilience suggests that the Great Red Spot represents a stable attractor in Jupiter's atmospheric dynamics, a pattern that the system naturally tends toward, even when disturbed. Understanding why the Great Red Spot has survived while other storms have faded is an important goal for atmospheric scientists. The answer probably involves the spot's size and depth, which give it a reservoir of energy and momentum that smaller storms lack. But the details are still being worked out, and Juno's observations of the spot's deep structure are providing crucial data for this research. Let us now look at another aspect of Jupiter that connects to its history and formation: the composition of its atmosphere. We have mentioned that Jupiter is made primarily of hydrogen and helium, the two lightest and most abundant elements in the universe. But the exact proportions of these elements and the abundances of trace species tell us much about how the planet formed and evolved. Hydrogen and helium were present in the solar nebula from the beginning, inherited from the molecular cloud that collapsed to form our Sun. If Jupiter had formed purely from this nebular gas, its composition would match that of the Sun, about 71% hydrogen by mass and 27% helium, with about 2% heavier elements. The actual composition of Jupiter differs somewhat from this solar mixture. Helium is slightly depleted in the upper atmosphere, suggesting that some of it has settled toward the planet's interior over billions of years. This helium rain, as it is called, would release gravitational energy as helium droplets sink through the hydrogen layer, contributing to the planet's internal heat. Evidence for helium rain is clearest on Saturn, where the depletion is more extreme. Jupiter shows a smaller effect, possibly because its interior is warmer and less favorable for the separation of helium from hydrogen. The degree of helium depletion provides information about the temperature history of the planet's interior. The heavier elements in Jupiter's atmosphere are enriched compared to the solar ratio. We have mentioned that water appears to be 2 to 3 times more abundant than in the Sun. Similar enrichments are seen for other volatile compounds like ammonia and methane. These enrichments indicate that Jupiter accumulated solid material as it formed, not just the gases of the nebula. The pattern of enrichment varies from element to element, which provides clues about the nature of the solid material Jupiter accumulated. Elements that freeze out as ices at low temperatures, like oxygen, carbon, and nitrogen, appear to be enriched by similar factors. Elements that condense at higher temperatures, like sulfur, show somewhat different enrichments. These patterns help constrain where in the solar system Jupiter accumulated its building blocks. If the solid material came from the outer solar system, where temperatures were cold enough for water and other volatiles to freeze, we would expect the pattern we observe. If Jupiter migrated from a different location, or if its growth involved material from different parts of the disk, the pattern might be different. The measurement of Jupiter's composition is an ongoing effort. Juno has made progress on some elements, but others remain difficult to measure from orbit. Noble gases like neon and argon are particularly useful tracers because they are chemically inert and do not form compounds. The Galileo probe measured some noble gas abundances, but the data were limited by the unusual location where the probe entered. A future atmospheric probe mission could improve on these measurements, descending to depths where the gases are well mixed and obtaining more comprehensive samples. Such a mission has been discussed but not yet approved. Until it happens, we must rely on the combination of Galileo's in situ measurements and Juno's remote sensing to piece together Jupiter's composition. The isotope ratios of elements in Jupiter's atmosphere provide another window into the planet's history. Isotopes are atoms of the same element with different numbers of neutrons, giving them slightly different masses. The ratio of heavy to light isotopes depends on the physical and chemical processes that affected the material before and during Jupiter's formation. Deuterium, the heavy isotope of hydrogen, is particularly important. The ratio of deuterium to normal hydrogen in Jupiter's atmosphere matches the solar ratio, suggesting that Jupiter's hydrogen came directly from the nebula without significant processing. This contrasts with comets and icy moons, which show enhanced deuterium abundances from chemical reactions at low temperatures. Other isotope ratios are harder to measure but equally informative. The ratio of nitrogen 15 to nitrogen 14, for example, varies throughout the solar system and can indicate whether nitrogen was delivered as gas or as solid compounds. Future measurements of these ratios will help refine our understanding of Jupiter's formation. Let us turn now to the future of Jupiter exploration and what we might learn in the coming decades. Juno will eventually end its mission, either through equipment failure or through intentional disposal into Jupiter's atmosphere. But other spacecraft are already on their way to the Jovian system, and more are being planned. The JUICE mission from the European Space Agency is currently en route to Jupiter, having launched in April 2023. After a series of gravity-assist flybys of Earth and Venus, it will arrive at Jupiter in 2031. The mission's primary focus is on Ganymede, the largest moon in the solar system, but it will also make extensive observations of Jupiter itself. JUICE carries a powerful suite of instruments for studying Jupiter's atmosphere, magnetic field, and radiation environment. It will observe from different vantage points than Juno, providing complementary data that will help complete our picture of the Jovian system. The mission is planned to last at least 3 years at Jupiter, with the possibility of extension if the spacecraft remains healthy. One of JUICE's key goals is understanding the habitability of Jupiter's icy moons. Ganymede, Europa, and Callisto all may harbor subsurface oceans, making them potential abodes for life. By studying the internal structures of these moons, their interactions with Jupiter's magnetic field, and their surface compositions, JUICE will assess the conditions in their hidden waters. NASA's Europa Clipper mission has a similar focus, but with particular emphasis on Europa. That moon's ice shell is thinner than Ganymede's, and its ocean appears to be in direct contact with a rocky seafloor. This makes Europa potentially more favorable for life, since chemical reactions between rock and water could provide energy sources for organisms. Europa Clipper launched in October 2024 and will arrive at Jupiter in 2030. Rather than orbiting Europa directly, which would expose the spacecraft to intense radiation, it will make nearly 50 close flybys while orbiting Jupiter. Each flyby will allow detailed study of a different region of Europa's surface and subsurface. The spacecraft carries ice-penetrating radar that will map the structure of Europa's ice shell, potentially detecting lakes of liquid water trapped within the ice. It also carries instruments to study the thin atmosphere, searching for plumes of water vapor that might erupt from the ocean below. If such plumes exist, they could provide access to ocean water without the need to drill through miles of ice. These missions represent just the beginning of what promises to be an exciting era of Jovian exploration. Proposals for follow-up missions are already being developed, including landers for the surfaces of Ganymede and Europa, and even submarines that could explore the subsurface oceans directly. The technology challenges are formidable, but the scientific rewards could be profound. A Europa lander would, face numerous obstacles, including the intense radiation environment, the uncertain nature of the surface terrain, and the need to survive landing on ice of unknown strength. But if successful, it could analyze surface materials directly, searching for organic compounds and other signs of habitability. The data from Europa Clipper will help design such a mission by revealing where the most scientifically interesting landing sites are located. For Jupiter itself, future exploration might include additional atmospheric probes that could descend deeper than Galileo did and sample more representative regions of the atmosphere. Advanced materials and communication systems might allow probes to survive longer and transmit data from greater depths, revealing more about the transition to liquid hydrogen and the metallic hydrogen layer below. Improved observations from Earth and near-Earth space will also contribute to our understanding. The James Webb Space Telescope has already observed Jupiter, providing new details about the planet's auroras and atmospheric composition. Its infrared capabilities complement the visible light and radio observations from other facilities, building a more complete picture. Ground-based telescopes with adaptive optics can now resolve Jupiter with remarkable clarity, approaching the resolution of some spacecraft images. A network of professional observatories and dedicated amateur astronomers maintains continuous watch on the planet, tracking changes in its atmosphere between the relatively infrequent visits by spacecraft. Now, let us step back and consider the philosophical implications of what we have learned. Jupiter is a world of superlatives, the largest planet in our solar system, with the strongest magnetic field, the most powerful storms, and the most complex system of moons. It has been visible in our sky since before humans existed, named for the king of the gods in Roman mythology. And yet, for all its majesty, it remains in many ways mysterious. We have learned enormous amounts about Jupiter in the past few decades, transforming it from a mysterious light in the night sky to a planet we can begin to comprehend. Spacecraft have orbited it, entered its atmosphere, and observed its moons in exquisite detail. Theories have been proposed, tested, and refined. The dim outlines of understanding have begun to emerge. And yet, the more we learn, the more we realize how much remains unknown. The interior of Jupiter is still largely hidden from our instruments, accessible only through indirect measurements. The processes that create its weather and drive its magnetic field are understood in outline, but not in detail. The history of its formation and evolution remains the subject of active debate. This is the nature of science. Every answer raises new questions. Every discovery opens new horizons. The universe is inexhaustible, and no amount of study will ever reveal all its secrets. But that is precisely what makes exploration worthwhile. The joy of science lies not in achieving final answers, but in the endless process of discovery itself. Jupiter will continue to surprise us. Future missions will reveal features we have not yet imagined. New theories will replace current ideas as observations accumulate. The planet that our ancestors saw as a wandering star will be understood in ever greater depth by our descendants. And through it all, Jupiter will continue its stately progress around the Sun, spinning through its 10-hour days and its 12-year orbits. The storms will rage. The magnetic field will pulse. The moons will trace their endless paths through the radiation belts. The planet will remain indifferent to our curiosity, as it has remained indifferent to everything that has happened on the small blue world where we make our home. But we will continue to watch. We will continue to send our machines to probe its secrets. We will continue to wonder at its majesty and puzzle over its mysteries. That is what we do. We are the species that asks questions, that reaches for understanding, that refuses to accept ignorance when knowledge is possible. Jupiter has been waiting for us for 4.5 billion years, and we have only begun to answer its call. As we near the end of our journey tonight, let us gather together the threads of what we have explored. We began at the cloud tops, that thin layer of color that is all we can see with ordinary light. We descended through layers of increasing pressure and temperature, through the weather deck where storms rage, down to where the atmosphere transitions from gas to liquid and from liquid to metal. We traced the magnetic field lines from the poles to the equator, following the currents of metallic hydrogen that generate the field and the charged particles that create the auroras. We visited the moons that orbit in Jupiter's shadow, from volcanic Io to icy Europa to giant Ganymede. We watched as Juno made its patient orbits, gathering data that has transformed our understanding. Jupiter is a world of wonders, a laboratory for studying conditions that exist nowhere else. It challenges our theories and rewards our observations with surprises. It connects us to the birth of the solar system and to the countless other giant planets scattered throughout the galaxy. The giant planet will continue to turn through the darkness long after we are gone. Its storms will continue to rage. Its magnetic field will continue to shield its moons from the worst of the radiation. Its gravity will continue to shape the paths of comets and asteroids throughout the solar system. Jupiter has been here since the beginning, and it will remain long after the end. But tonight, we have visited it in imagination. We have soaked in its wonders and marveled at its mysteries. We have learned something about a world we can never touch, and in doing so, we have learned something about ourselves. That is the gift of exploration. It expands our minds beyond the narrow confines of daily life. It shows us that the universe is grander and stranger and more beautiful than we could ever imagine. It reminds us that we are part of something vast and ancient and ongoing. The stars are wheeling overhead as you rest now. Among them, if the season is right, you might see Jupiter shining with its steady light. It has shone that way for billions of years, and it will shine for billions more. But tonight, you know a little of what lies beneath those clouds. You have traveled in imagination to depths no human will ever reach. You have touched the heart of a giant. Let that thought carry you into sleep. The cosmos is vast, but you have explored a piece of it tonight. The mysteries are endless, but you have glimpsed a few answers. Rest now, fellow traveler. The universe will be waiting when you wake, patient and magnificent, ready for the next journey. And somewhere out there, Jupiter continues to turn. The storms rage on. The secrets wait to be discovered. And the adventure of understanding continues, one orbit at a time. The planet that the ancients named for the king of the gods deserves that title still. Jupiter rules the outer solar system with its gravity, shapes the fates of worlds with its influence, and holds wonders beyond counting in its infinite depths. We have only begun to know it, and a lifetime of study would only scratch the surface. But that is enough for tonight. You have journeyed far and learned much. Let your mind drift now among the stars, carrying with it the images and ideas we have explored, the colorful bands of clouds, the raging, great red spot, the geometric patterns of polar cyclones, the invisible magnetic field linking planet and moon, the crushing depths where hydrogen becomes metal, the fuzzy core bearing witness to ancient collisions. All of this exists right now, spinning through the void 500 million miles from where you rest. It has existed for eons, and it will exist for eons more. We are privileged to live in an age when we can begin to understand it, when robotic emissaries carry our curiosity to worlds we cannot visit, when the patient work of science reveals what was once hidden. Take comfort in that tonight. The universe makes sense. Not completely, not yet, but enough that we can ask questions and find answers. Enough that we can send spacecraft to orbit distant worlds and peer beneath alien clouds. Enough that we can lie in our beds and imagine sinking through the atmosphere of a giant planet, touching with our minds what our bodies can never reach. Sleep well now. Let the wonders we have contemplated settle into your dreams. When you wake, the world will be waiting with its ordinary concerns. But you will know somewhere in the back of your mind that beyond this world lies another, a world of storms and secrets, of crushing depths and soaring auroras. Jupiter, the giant, the king, the mystery that calls to us across the darkness. And we will keep answering that call. We will keep asking questions and seeking answers. We will keep sending our machines and our imaginations to places we cannot go ourselves. That is what we do. That is who we are. Good night, fellow traveler. May your dreams be filled with wonders, and may you wake refreshed, ready to explore whatever mysteries tomorrow brings. The giant planet turns, the cosmos continues, and the journey goes on. The stars above your head tonight are the same stars that shone when Jupiter was young. They watched as the solar nebula collapsed and ignited into a star. They watched as the planets coalesced from the swirling disk of gas and dust. They watched as Jupiter grew to its enormous size, capturing gas and shepherding the formation of its moons. Those ancient lights have witnessed it all, and they will continue their vigil long after our sun has faded. There is something comforting in that continuity. The universe is old beyond our comprehension, and it will endure beyond our imagining. We are brief sparks of awareness in an immense darkness, but in our brief time we have managed to understand something of the grandeur that surrounds us. We have named the stars and charted the planets. We have sent our instruments to touch distant worlds. We have begun to unravel the mysteries that once seemed forever beyond our reach. Jupiter was a mystery to our ancestors. They saw it wander among the fixed stars and named it for the mightiest of their gods. They watched its movements and used them to mark the passage of years. But they could never have imagined what we now know. The storms raging across its face, the moons orbiting in its shadow, the crushing depths hiding secrets billions of years old. We have inherited their wonder and added to it our knowledge. We have taken the questions they asked and begun to find answers. And we have raised new questions that they never thought to ask. Questions that our descendants will spend their lives exploring. That is the legacy of science. Each generation builds on what came before, reaching a little farther, seeing a little more clearly. The universe reveals itself slowly, one discovery at a time. And each discovery opens new doors, new possibilities, new wonders to explore. Jupiter will be waiting for all of them. The giant planet is patient. It has circled the sun over 400 times since Galileo first saw its moons, and it will circle hundreds of times more before our explorations are complete. Every orbit brings new opportunities to observe, new chances to understand. The planet that seemed so mysterious in Galileo's telescope has become more familiar, but it has not become less wondrous. If anything, the wonder has deepened. The more we learn about Jupiter, the more remarkable it seems. The complexity of its atmosphere, the power of its magnetic field, the intricate dance of its moons, all of these exceed what we might have imagined before we looked closely. Jupiter is grander than our ancestors dreamed, and grander still than we can fully comprehend even now. That grandeur will remain when you wake tomorrow. Jupiter will still be there, shining in the night sky or hidden below the horizon, continuing its eternal journey around the sun. The storms will still be raging. The magnetic field will still be pulsing. The moons will still be tracing their ancient paths. And somewhere, in laboratories and observatories around the world, scientists will be studying the data, building the theories, planning the missions that will reveal the next layer of secrets. The work goes on, day after day, year after year. It is slow work, patient work, work that requires the efforts of many people over many generations. But it is work that matters, because it expands the boundaries of what we know and what we can imagine. You are part of that effort tonight. By contemplating Jupiter, by learning something of its nature, you have joined the community of those who seek to understand. You have looked beyond the immediate concerns of daily life and touched something vast and timeless. You have exercised that capacity for wonder that makes us human. Carry that wonder with you into sleep. Let it color your dreams with images of swirling clouds and distant moons. Let it remind you that the universe is large and you are part of it. Let it comfort you with the knowledge that there are always more mysteries to explore, more wonders to discover, more journeys to take. The night is deep now, and the stars are bright. Somewhere among them, Jupiter is shining. It has been shining since before there were eyes to see it, and it will go on shining long after we are gone. But tonight, in the quiet of this moment, it shines for you. Rest well, traveler. The cosmos will keep turning while you sleep. The giant planet will keep guarding its secrets, revealing them slowly to those patient enough to look. And tomorrow, or the day after, or sometime in the years to come, another piece of the puzzle will fall into place. Another mystery will yield to understanding. Another wonder will be added to the catalogue of things we know. That is the promise of exploration. That is the gift of curiosity. That is why we look up at the stars and ask our questions and refuse to stop until we find our answers. Jupiter is waiting. It has always been waiting. And it will wait for you to return whenever you are ready for the next journey. Good night. Sleep deep. Dream of distant worlds. And when you wake, remember, the universe is wonderful, and you are part of its story. The journey continues. The mystery endures, and the giant planet turns on through the endless night, keeping its secrets and sharing its wonders with all who take the time to look. May peace find you now. May rest restore you. And may the cosmos always fill you with awe. Sleep well, fellow traveler, until we meet again among the stars. There is one more aspect of Jupiter we have not yet explored in depth, and it deserves our attention before this journey ends. We have spoken of the planet's atmosphere, its interior, its magnetic field, and its moons. But we have not fully considered what Jupiter means for our understanding of planets throughout the universe. When astronomers began discovering planets around other stars in the 1990s, Jupiter became even more important than it had been before. Suddenly, the only giant planet we could study in detail became a reference point for understanding thousands of distant worlds. Every exoplanet discovery was compared to Jupiter, either because it resembled our local giant, or because it differed in significant ways. The first exoplanets discovered were hot Jupiters, giant planets orbiting impossibly close to their parent, stars. These worlds challenged our theories of planet formation, since no giant planet could have formed in such scorching environments. They must have migrated inward from more distant orbits. a process that implied a more dynamic history for planetary systems than anyone had expected. Our own Jupiter may have migrated as well, though not as dramatically. The Grand Tack hypothesis suggests that Jupiter moved inward toward the Sun early in the solar system's history, then reversed course and migrated back outward. This migration would have scattered material throughout the inner solar system, potentially explaining the relatively small mass of Mars and other features of our planetary architecture. Whether or not the Grand Tack occurred exactly as proposed, the idea that giant planets can reshape entire solar systems is now well established. Jupiter's influence extends far beyond its immediate vicinity. Its gravity has affected the orbits of every object in the solar system, from the asteroid belt to the Oort cloud. Understanding how Jupiter exerts this influence helps us interpret the configurations of planetary systems around other stars. The composition of exoplanet atmospheres is another area where Jupiter serves as a guide. When astronomers detect water vapor or methane in the atmosphere of a distant giant planet, they interpret those measurements by comparison to what we know about Jupiter. The abundances and distributions of molecules in Jupiter's atmosphere set expectations for what we might find elsewhere. Some exoplanets have proven quite different from Jupiter, with compositions and structures that challenge our models. Super-Jupiters, giant planets several times more massive than our local example, may have different internal structures and atmospheric dynamics. Mini-Neptunes, smaller than Jupiter but larger than Earth, occupy a size range with no solar system equivalent. Each new discovery expands our understanding of what planets can be, but Jupiter remains the touchstone. It is the giant planet we know best, the one we have studied with spacecraft and Earth-based telescopes for decades. Every model of giant planet structure is tested first against Jupiter, before being applied to more distant worlds. Every theory of atmospheric dynamics must explain Jupiter's jets and storms before it can claim to be general. This is why continued exploration of Jupiter matters not just for understanding our own solar system, but for understanding the universe as a whole. The more we learn about our local giant, the better we can interpret observations of giants elsewhere. The data from Juno and future missions will echo through exoplanet science for generations. Consider the question of clouds and hazes in giant planet atmospheres. Jupiter's visible clouds are just the outermost layer of a complex atmospheric structure, with different chemical species condensing at different depths. Ammonia ice forms the highest clouds. Ammonium hydrosulfide may form a layer below that. Water clouds likely exist even deeper, hidden from direct view. Exoplanets have their own cloud structures, which we can begin to glimpse through transit observations and direct imaging. When a planet crosses in front of its star, some of the star's light filters through the planet's atmosphere, carrying signatures of the molecules present. When we can image a planet directly, we can analyze the light it reflects or emits. In both cases, clouds affect what we see. Understanding Jupiter's clouds helps us interpret these observations. The vertical structure of the atmosphere, the chemical reactions that occur at different levels, the ways that clouds form and dissipate. All of this applies, with modifications, to atmospheres around other stars. Jupiter is our laboratory for atmospheric physics at giant planet scales. The same is true for magnetospheres. Jupiter has the largest and most powerful magnetosphere in the solar system, and studying it has taught us much about how magnetic fields interact with plasmas and radiation. This knowledge applies directly to exoplanet magnetospheres, which we cannot observe directly, but which may play important roles in shaping planetary environments. A strong magnetic field can protect a planet's atmosphere from erosion by stellar winds. It can channel charged particles away from the surface or the tops of clouds. It can create radiation belts that affect the habitability of nearby moons. All of these effects depend on the strength and configuration of the field, which we can only estimate for exoplanets by analogy to what we know about Jupiter and Saturn. Some researchers have even proposed that magnetic field detections could serve as biosignatures, since life on Earth contributes to our planet's magnetic field indirectly through the water cycle and other processes. Whether this applies to other worlds is unknown, but Jupiter's magnetic field provides context for thinking about the question. The moons of Jupiter also have analogues around exoplanets. We cannot yet detect exomoons directly, but there is no reason to doubt that they exist. Giant planets should capture smaller bodies and accrete circumplanetary disks, just as Jupiter did in the early solar system. The moons that form or are captured will have their own geological and potentially biological histories. Europa is the prime example of how a moon can be habitable even far from its parent star. The tidal heating that powers its subsurface ocean could operate around any giant planet with the right orbital configuration. Ice-covered ocean worlds may be common throughout the galaxy, perhaps more common than Earth-like planets in habitable zones around their stars. If life exists in Europa's ocean, or in similar oceans elsewhere, it would have profound implications for the prevalence of life in the universe. Jupiter's moons are the most accessible examples of this type of environment, and studying them prepares us for the day when we might detect signs of habitability around distant stars. All of these connections elevate Jupiter's importance beyond its intrinsic interest. The planet is not just a local curiosity, but a key to understanding the cosmos. Every measurement Juno makes, every observation from Earth-based telescopes, every theoretical advance in understanding Jupiter's structure and dynamics contributes to a larger project of comprehending planets wherever they are found. That project will continue long after the current generation of scientists has retired. It will continue long after the current spacecraft have completed their missions. It will continue for as long as humans remain curious about the universe and capable of exploring it. Jupiter will be there, patient and magnificent, waiting for each new chapter of discovery. The night has grown late now, and the stars have wheeled further across the sky. Perhaps Jupiter has set below your horizon, or perhaps it still gleams among the fixed points of light. Either way, it continues its orbit, indifferent to whether we watch or sleep. The planet needs nothing from us. But we need it, in ways both practical and profound. We need Jupiter as a laboratory for studying physics under extreme conditions. We need it as a reference point for interpreting distant worlds. We need it as a guardian that has shaped our solar system's history. And we need it as a source of wonder, a reminder that the universe contains marvels beyond our daily experience. Tonight, you have contemplated some of those marvels. You have imagined descending through alien clouds into crushing depths where matter transforms into exotic states. You have traced magnetic field lines across millions of miles of space. You have visited moons with volcanoes and oceans, worlds within a world. You have touched, in imagination, a planet that has been waiting for us since before the Earth existed. That touch connects you to every other person who has ever looked up at Jupiter and wondered. The Babylonian astronomers who tracked its movements, the Greek philosophers who gave it its name, Galileo with his primitive telescope, the engineers who built Juno, and the scientists who pore over its data. All of them have been part of the same long conversation with the cosmos, a conversation that you have now joined. The conversation will continue tomorrow and the day after, and for all the days to come. There will always be more to learn, more to discover, more to wonder at. Jupiter will always have more secrets to reveal to those patient enough to look, and the universe will always be there, vast and old and magnificent, waiting for us to ask our next questions. But for now, rest. Let the thoughts we have explored settle into your mind like sediment settling through Jupiter's atmosphere, layer upon layer of wonder accumulating into something solid and lasting. You do not need to remember every detail. The important thing is the feeling, the sense of connection to something larger than yourself. That feeling is what drives exploration. It is what makes us look up at the stars instead of keeping our eyes on the ground. It is what sends spacecraft across billions of miles and keeps scientists working through long nights in their laboratories. It is the fundamental human impulse to know, to understand, to reach beyond our limitations. You have honored that impulse tonight. You have reached, in imagination, for a world you can never physically touch. You have added your curiosity to the sum of human wonder. You have become, in a small way, an explorer. Now let that explorer rest. The journey has been long, from the bright cloud tops to the dark metallic depths and back again. You have earned your sleep, and when you wake, the universe will still be there, still turning, still full of mysteries to solve and wonders to discover. Jupiter will still be there too, shining in its place among the stars, keeping its ancient secrets and slowly revealing new ones to those who care to look. The giant planet endures, the cosmos continues, and the story goes on, with or without us, forever and ever, without end. Good night, sleep deep, and may your dreams be filled with stars. The night embraces you now like the atmosphere of a distant world, gentle and encompassing. Let yourself sink into it as we imagine sinking through Jupiter's clouds, layer after layer of rest accumulating around you. The worries of the day are the thin upper atmosphere, and you are descending past them now into regions of deeper quiet. The stars watch over you as they have watched over every sleeping creature since life began on Earth. They are ancient beyond comprehension, and they will endure beyond imagination. Among them, Jupiter follows its endless path, a wandering light that your ancestors saw and that your descendants will see. In that continuity, there is comfort. You are part of something vast. You are connected to a universe billions of years old and billions of light years wide. You have contemplated tonight just one small part of that immensity. One planet among countless planets. One story among infinite stories. But that one part is enough. That one story is enough. It connects you to everything else. Sleep now. Let the cosmos hold you. And know that when you wake, the adventure will be waiting to continue. There are always more worlds to explore, more mysteries to solve, more wonders to contemplate. The journey never truly ends. It only pauses now and then for rest. Good night, fellow traveler. The stars are shining, Jupiter is turning, and all is well with the universe. In these final moments before sleep claims you completely, let one last thought drift through your mind. Of all the places in this vast universe, of all the worlds spinning through the darkness around countless suns, you happen to live in a solar system with Jupiter. This magnificent giant has been your companion since before you were born. It has hung in your sky on summer nights and winter evenings, a steady point of light among the wheeling stars. Most people never think about Jupiter. They see it, perhaps, without knowing what they see. They might notice a bright star that does not twinkle, brighter than anything else in that part of the sky. but they do not stop to wonder what it is, what lies beneath its clouds, what stories it might tell if we could understand its language. You are different now. You have stopped to wonder. You have taken the time to learn, to imagine, to explore. Jupiter will never look quite the same to you again. When you see that bright point of light, you will know something of what it represents. You will remember the storms and the moons, the magnetic fields, and the metallic hydrogen, the ancient history written in its composition and structure. That knowledge is a gift, one that cost nothing to acquire but that enriches your experience of the universe immeasurably. You are more connected to the cosmos than you were before this journey began. You understand your place in the grand scheme of things a little better. You have added to your internal map of reality, filling in details that were blank before. This is what learning does. This is what exploration accomplishes. Each new piece of knowledge makes the universe a little more familiar, a little more comprehensible, a little more wondrous. The mystery does not decrease, it deepens. The more we know, the more we realize how much remains unknown. But that is not discouraging. It is exhilarating. It means the adventure will never end. Jupiter will always have more to teach us. The universe will always have more to reveal. And we will always have more capacity for wonder, more joy in discovery. These qualities have carried us from caves to spacecraft. They will carry us further still. But for tonight, you have traveled far enough. Rest now in the knowledge that you have touched something ancient and magnificent. Rest in the peace that comes from being connected to something larger than yourself. The giant planet turns on through the night. The stars shine on, and you drift into sleep, carrying with you the memory of a journey to the heart of Jupiter. Sweet dreams, traveler. The cosmos awaits your return.